Hi Wildcats. This is a example problem or scenario with multiple problems from Unit 6, Focus Question 2, so looking at different aspects of free fall acceleration. So I've already drawn my picture, and they tell me that an object or cannonball is fired straight up with an initial velocity of 30 meters per second atop a 100-meter cliff, and then they ask us a bunch of different things about it. So I like this problem. I know it has multiple parts, but at the same time it allows us to look at a number of aspects of free fall and some things that we know or can assume about its motion. So the very first thing it says is, how long does it take? So we are looking for change in time. So how long does it take to reach the top of its motion? So in other words, here. Well, we know that it's initially fired with positive 30 meters per second, a velocity of 30 meters per second in the positive direction. We know that it is on Earth and in a vacuum because we're going to assume those. So its acceleration or its velocity changes at a rate of 9.81 meters per second squared. And then we want to know, we know that when it gets to the top of its motion, its velocity is 0 for a second. So at this point, its velocity is 0. So I can look at this as a problem, and really I'm looking at it as how long does it take to get from there, from where it's initially launched, to the top. And so I can call that V final is 0. So this is everything I know. I don't know anything about the displacement, how high that is that it's going to go. So is there a kinematics equation that I can use that doesn't involve displacement but involves all those other features like time and velocity? And so yes, there is. The equation that we're going to want to use is V final is equal to V initial plus acceleration times time. So this one has no displacement. So as always, I'm going to do the algebra first. So we are going to subtract V initial from both sides. So I end up with V final minus V initial is acceleration times time. I can divide both sides by acceleration. So that's gone. So if I look at this, it's going to be the time it takes to get to the top where its velocity is 0 is V final minus V initial divided by the average acceleration of it. So in this case, V final we see is 0 meters per second minus its initial velocity, which is 30 meters per second, all divided by minus 9.81 meters per second squared. And so this actually is going to work out well. So if we look at this, I've got negative 30 divided by negative 9.81. So that's going to be a negative divided by a negative is a positive. Since time is a scalar, it wouldn't make sense to have negative or a direction. So really it's going to be 30 divided by 9.81, which is going to give me 3.06 seconds. So it takes 3.06 seconds to get to the top. So that's the first part. The next part is, what is the maximum height that the object reaches? Okay, so this one's even easier because now I know its initial velocity, its final velocity, its acceleration, and I know how long it takes to get to the top. So I can pick any kinematics equation that has displacement in it. The easiest one for me looks like it's going to be displacement is equal to 1/2 V initial plus V final times change in time. So this allows me to just solve 1/2 times V initial, so 30 meters per second plus 0 times 3.06 seconds. So when I put that into my calculator, I end up with 30 times 3.06 times 0.5, and it looks like it has a displacement of 45.9 meters. So let's see, how long does it take? Well, it's going to take 3.06 seconds to get to the top. The top of its motion is 45.9 meters. And so then it says, what is the velocity of the object when it gets back to the student? So since it's going straight up and then straight down, at some point, this point right here, it will be at the same vertical position that it started at. And so there's a couple ways that we can approach this problem conceptually as well as mathematically. Okay, So, as I was saying, there's a couple ways that we can do this. One is, since we know a bunch about this now, we know that it takes 3.06 seconds to get to the top. And so therefore it's going to take 3.06 seconds to get back from the top down to here. So we could solve this as a different problem where we're looking at its motion from the top back down, so to here. And so we would call this V initial, where this is 0 meters per second. And this is V final. And then we know its time. The time, well, we always know acceleration, so minus 9.81 meters per second squared. Now we also know the time about this, that it is 3.06 seconds to come back down. And if we really wanted to, we could even say everything that it is 45.9. So maybe the easiest way to solve for this is just solve for V final. So V final, using our kinematics equation, is equal to V initial plus acceleration times time. The initial is 0, so we can get rid of that. So it works out to be acceleration, which is minus 9.81 meters per second squared, times time, which we said it's going to take the same time to rise as it is to fall, is 3.06 seconds. So V final is going to be 9.81 times 3.06, and you end up with 30.0 negative meters per second. So 30 meters per second in the negative direction. So this is our answer proven mathematically, but this is an important concept to understand as well, is that at any vertical position, the object will have the same velocity, the same speed as it did on its ascent, but it'll be the opposite direction because it's coming down. So if at this position when it was launched, we know it was launched at 30 meters per second in the positive direction. When it gets back there, it'll have a velocity of 30 meters per second in the negative direction. So that's something that we can just know, and we saves us from having to solve for it every time. So it would be minus 30 meters per second. All right, so now that we know all these details, we can figure out the last part of this problem, which is what is the velocity of the object when it hits the ground. So in other words, we are looking for its velocity at this point right here. All right, so let's see, what can we do? We know some things. We know that this displacement is 100 meters. We know that its acceleration is minus 9.81 meters per second squared. We also know that its velocity at this point is 30 meters per second down. We want to find V final. So let's see. Let's write down everything we know. We know the displacement at that point is 100 meters, and it's down, so negative 100 meters. We know acceleration is minus 9.81 meters per second squared. And we know its initial velocity, because I'm just looking at this region right here, right? Because I have a velocity at the beginning and I'm looking for the velocity at the end. So we'll call that minus 30 meters per second. And then V final is what we're looking for. So really the only thing we don't have is time. So I need an equation that does not have time in it. I've got one where I can use V final squared is equal to V initial squared plus 2a delta x. All right, so let's see. We can just plug in, right? The only thing we need to do is square root both sides to get rid of this square. So V final is equal to the square root of V initial squared plus 2a delta x. So if I plug in those numbers, that is going to be minus 30 meters per second squared plus 2 times, let's see, my acceleration here is minus 9.81 meters per second squared, and my displacement is 100 meters, and it's in the negative direction. So let's just check my signs here. If I'm negative 30 and squared, so that's going to give me a positive number, and negative 100 times negative 9.81, that's going to give me a positive number. So I should be able to get a square root that works out here. I have 30 squared is 900, plus I'm going to take 2 times 9.81 negative times 100 negative, and that will give me the square root of 2,862. When I take that, I end up with 53.5 meters per second. And if we remember from math, it's actually going to be plus minus because I've got the square root. So we need to use our logic here and recognize that since it's here, its velocity will be going down. So the answer that makes sense, and the correct answer, is minus 53 meters per second, or 53 meters per second in the negative direction. So now we have V final. We have everything here except for time. Let me write this over here. So minus 53.5 meters per second. The only other thing it asks us for is what is the total time. So that would be time from here to the top, here back to where it started, and then this time. So we solve for the time up, right? It is 3.06 seconds. So let me just erase some of this. Okay. So we know that from here to the top is 3.06 seconds. From there back down is 3.06 seconds. And then so really the only time we don't know is this 100 meters that it's traveling. So we need a kinematics equation that has time. We know everything else. We now know V final, it's 53.5. So I think the easiest equation for this is going to be V final is equal to V initial plus acceleration times time. So I'm looking for time. So V final minus V initial is equal to acceleration times time. Divide both sides by acceleration. Gone. So time is equal to V final minus V initial divided by acceleration. V final we know is minus 53.5 meters per second, minus its initial velocity, which is from here to here, is minus 30 meters per second, all divided by minus 9.81 meters per second squared. So minus 53.5 minus a negative 30 divided by negative 9.81 gives me a time of about 2.4 seconds. So this is 2.4 seconds. So my answer would be 2.4 plus 3.06 plus 3.06. So the whole time from here where it is launched all the way back to where it ends is going to take 8.52 seconds. And there it is. That is a lot of different steps, but at the same time it covers a lot of the assumptions that we talked about an object in free fall having. So I hope that helps as you prepare for your assessment on Monday and Tuesday.